My name is Ciaran Kennedy. I'm just finishing up a PhD here at NUIG, and my professors are Sean Lean and Dr. Crowell O'Brady, and we've been investigating the fatigue of GFRP in seawater, because we think that's going to be a good material for use in ocean energy devices. So, here we go. Okay, so just a quick overview of the material itself. The glass fibres used in fiberglass are actually very small in diameter, and that by stretching them out to these very tiny dimensions, you can well, essentially what happens is that the flaws that are in bulk glass get distributed at very far apart, and basically they become they're no longer important for the strength of the material. So then there's a polymer matrix that's injected around the glass fibres, and that helps to distribute the load among all the glass fibres, and it kind of turns it into a solid material. And then the other material that kind of gets forgotten that's in there is there's a size compound that's applied to the fibres as they're drawn, and this size protects the glass fibres during processing, and it also has a silane molecule in there that helps to bond the polymer onto the glass surface, and it protects the glass surface from the effects of moisture. If you don't have that, the moisture tends to cause stress corrosion cracking of the glass fibres. So the individual plies of glass fibre are very strong in the fibre direction, but they're quite weak perpendicular to that. So invariably, for most applications, we end up laminating them with the fibres in various directions in order to get a useful material. So the only thing about that then is that if you go to do design on those materials or using those materials, it can become kind of daunting. You can end up there seems to be an endless number of possible permutations and combinations. So I've put a couple of kind of popular laminates that up here so that we could discuss them. And the first one is quasi-isotropic material, and it has basically fibres in all directions. Well, it has in 4 directions: 0, 90, plus or minus 45, and that makes the material equally strong in all directions, and equally stiff in all directions. And so it's useful for cases where the loads are kind of multi-directional in nature, or maybe for something simple where you just want to do a simple analysis and you don't want to go, creating a complicated analysis. So that can be a very useful material. So that's and that material is shown here on the graph. It has a fatigue strength of between 250 MPa and 125 MPa. So the next kind of useful laminate to talk about is a laminate where we align about 55% of the fibres in the direction of the kind of nominal load, and the rest of the fibres are usually oriented at plus or minus 45 degrees to that. So that material is useful for kind of unidirectional loading, or unidirection, mostly where you kind of know the direction of the load, but maybe there's some multi-axiality or a little bit of uncertainty about where it's going to go. So a typical application for this that most of you would know would be on wind turbine blades. And this material then has a fatigue strength of between 500 MPa and 200 MPa. So the other thing then is just a couple of notes about immersed use itself. It is important when you're making GFRP for use in immersed applications that you use a good manufacturing process, because voids and flaws are certainly magnified by the effects of water. The other thing I would say is it's a good thing to target somewhere between 50 and 60% of fibre volume fraction in the materials, and that's on one hand gets you a good strong material. On the other hand, if you start to go much above 60%, you start to have problems with the fatigue strength of the material, even though the kind of static tensile strength would look good on the data sheet. I would tend to stay below 60%. And the final thing I'd mention here is that it's a good idea to post-cure the laminate, and that's a process where after the material has been kind of set for maybe 24 hours, you heat it up to maybe 80 degrees centigrade, and that allows the final cure to take place, and it kind of gets the properties in the right place for you. Now, there are some other GFRP materials that are also useful. In particular, vinyl ester is the least affected by water saturation, but it does have a lower fatigue strength to start off with than epoxy. So you're going to lose maybe 15 to 30% of your fatigue strength by going to vinyl ester. Now, it's a little bit cheaper than epoxy, so there may be a trade-off there. In some situations, it may be good to use. There's also polyester, which is actually, it's kind of been around the longest, and it's certainly used a lot in boats and such. For high performance immersed applications, it has problems with osmosis and hydrolysis when it's water saturated, so it's really not recommended. So for me, when I was doing the research, to investigate the effects of water immersion, I started out by putting some material samples into a warm water bath to accelerate the water absorption process. And basically, water absorption into a polymer is a diffusion process. And so by using the Arrhenius law, we can get an estimate of what sort of acceleration we're going to get of the diffusion. And it kind of depends on what low temperature you pick, and what the temperature of the water is. And in this case, I've decided that essentially the sea temperature around Ireland will be about maybe 12 degrees on average, and and by using a water bath temperature of 30 degrees, I get an acceleration factor of 10. I also had some water or some samples in room temperature water, and you can see that that actually has an acceleration factor of maybe as much as 3, which maybe you might not expect. I guess one thing I would say is that it is important to, in your water bath, to have it kind of stirred and maintain it at a constant temperature, because you know, even you can see the temperature differences here are not very big, and so if you get a gradient in your water tank, that's going to have an effect on your results. So in terms of the percent of water absorbed by my coupons, two different types. I had the vinyl ester E-glass and the epoxy E-glass. You can see the vinyl ester absorbed very little water at all, only 0.2% over 2 years. Whereas the epoxy E-glass absorbed a little over 0.6%. And that would be pretty typical of the absorption characteristics of these materials, although I found them, both of my experiments showed I actually got significantly less water absorption than was reported elsewhere in the literature. Now, the reason for that, well, I think the main reason is probably that the particular materials, you know, when I was looking for materials to use here, I chose materials that are specifically designed for water immersion. So the vinyl ester E-glass that I used was Scott Bader Cystic, and then the epoxy was Ampreg by Gouret. So I did some fatigue testing then of the coupons on a servohydraulic test machine, and we tested them in what we call tension mode here. So we went sort of maybe between 200 MPa and 20 MPa in kind of a cycle about 5 times a second. And you can see that one of the things we learned during this process was that it is important to keep the samples immersed while they're being tested, because otherwise they have a tendency to dry out, and as they dry out they regain their strength. So we came up with 2 different types. First of all, I started out with this kind of nice looking but slightly complicated setup, and eventually I found that this nice simple plastic bag and some waterproof tape worked just as well. So that's what research is, I suppose. So in terms of results then, over here on the right there's a graph that plots the effect of the water on the epoxy e-glass. And the top line here is the dry fatigue strength of the material, and then right under it here is the fatigue strength of that saturated, water-saturated material when it was tested after that 2-year immersion. So, and you can see here that there's kind of a 20 to 25% loss in strength when the material becomes saturated at the high stress end of the curve, and down here is about 8% loss in strength at nearly 1 million cycles. Now, I've also done some tests on vinyl ester, not as many, and but like I mentioned earlier, the water seems to have very little effect on vinyl ester, and in this case here at 180 MPa, I've found that there's just almost no difference between a dry coupon and a saturated coupon. So those are the quasi-isotropic results. And so to think about the effect that it have on other laminates, I've got on the graph here, I've shown this is the data on the quasi-isotropic material down here at the bottom of the graph, and up here then I've found some data that is from some testing done by the team at Montana State University, and they've tested that unidirectional material in both wet and dry, and I've shown their results there. Just the question is, what about that laminate in between? So what I did was I've taken that data and I've normalized it by the dry fatigue strength at 1,000 cycles, and you can see that it comes out with a very nice pattern here, where you can see that that at the high stress end of the curve, that both the unidirectional material and the quasi-isotropic material both essentially lose 20% of their fatigue strength when they're water saturated, and then that loss in strength is reduced steadily until somewhere up between 2 million and 50 million cycles. The difference between the two material, between the wet and dry, completely disappears. So the other thing that we monitored during the fatigue testing was the modulus or stiffness decay of the material, and in particular what we monitored was what we call fatigue modulus. And if you see, this is the stress-strain response of the material, and that's the very first thing, and then there's the first loop there as the material goes around, and then you can kind of see that as the fatigue cycles go on, we get this, it kind of leans over a little bit and we get a lower stiffness. And when I plot all that data, and I've plotted 3 different load levels on the graph, and you can see that essentially we get about a 25 to 30% stiffness loss in the material. This is actually during dry fatigue testing, and so there's kind of it gets to the same place. It gets there by a slightly different path. The the high stress material loses quite a bit at the beginning and then drops fairly steadily away till it fails. The low stress testing don't lose so much, but then it kind of gets into this thing where there's a long period where it's steadily losing stiffness. I guess the interesting thing for me is that if I take and put the wet results on top of the dry results here, you can see that there's just about no difference in the response or in the evolution of the fatigue modulus between wet and dry samples. So I think this shows that really there's just about the only thing that you can see here is that the wet material stops sooner, and that's because it fails earlier. But other than that, it's very, very similar. So in conclusion then, I would say that I've kind of talked about a couple of popular laminates as a starting point for design. The quasi-isotropic material is for the multidirectional loads, and that has a fatigue strength between 250 and 125 MPa. For unidirectional loads then, if you put about 55% of the fibres in the direction of the primary load, and then that has a fatigue strength between 500 and 200 MPa. The other thing is that, you know, if you choose the right resin and have a good manufacturing process, you can get the amount of water absorbed to be quite low, and I certainly think that's a good idea. In terms of the wet fatigue strength then, I've shown that epoxy has about a 20% decrease at 1,000 cycles to failure, and essentially at some point in there's no difference between, at some point in the high cycles, there's no difference between the wet and dry material. And for me, for the testing I've done, certainly the final ester seemed to be, there was no decrease due to saturation. And then the other thing I've shown is that the stiffness, that there's no additional stiffness degradation due to water immersion. Okay, so thank you very much for your attention.